Good morning, everybody. This is Cassie Stumo. I am the marketing specialist here at EAC. Thank you for joining us today for our Never Before Seen webinar. We'll start off today with an introduction of EAC from Vinny, our Associate Account Manager of all things ANSYS, and then our Technical Account Manager and ANSYS expert, Scholl, will show us how we can use ANSYS Mechanical to predict fatigue cracks with finite element analysis. Everyone gets a recording of the session pending any technical difficulties. Please feel free to ask questions along the way and we'll answer them after the presentation. I will hand things over to Vinny now to get a quick EAC intro for those of you who do not know who we are.
Thank you, Cassie. So I will get things started with some background of who EAC is and what it is we do here. So our mission here is to transform the way that companies design, manufacture, connect to, and service their products. Now, some of you that have worked for us for several years have probably heard us say this before, but I'm sure there are some of you out there that might be wondering, what the heck does this mean? Well, Rod, if you can go to the next slide, it means that everything that we do to help companies build better products is connected throughout both your organization and ours. We don't really see ourselves as just one other value-added software reseller. We see ourselves as a highly trusted business consultant. If you just look at all the areas that we're capable of providing support, we're Platinum PTC partners, preferred ANSYS partners, Formlabs partners, and on the engineering side and services side, we have a full staff of engineers that can assist with any product development consulting or any other service work questions that might arise as you're trying to get some of your new designs out the door. We also have a full implementation staff that is ready and able to come on site to ensure that any PLM launch that you have is nothing short of successful. We're headquartered in Minneapolis, but we are also spread throughout the country to ensure that we will always have someone local that you can count on to come on site when it's needed in a pinch. Go ahead, Rod. Now, a little bit more about the ANSYS side of things. Most of you, when you hear the word ANSYS, you probably immediately think simulation, and that is exactly what ANSYS wants to hear. They put forth a great effort since they were founded in 1970 to do one thing and to be the best at it, and that's simulation. This is the only thing that they focus on, and it shows throughout their entire organization. Their customer support system is completely unrivaled with over 450 PhDs on staff in over 70 locations in 40 countries. I've actually heard firsthand from some of our applications engineers at ANSYS that they like getting difficult problems to solve because they enjoy the challenge. If you have a problem, they would love to take on a challenge and try to help you find a solution. Now, if you choose to focus on one thing, you'd better be really good at it. And ANSYS's reputation definitely backs them up here, as some of the data on this slide shows. They're 3 times larger than their nearest competitors, and 96 of the top 100 Fortune 500 industrial companies use ANSYS. I like to repeat that one just to let it sink in. 96 of the top 100 Fortune 500 companies are using ANSYS. That's an incredible statistic. And a big reason for this is that they're completely CAD agnostic and can truly work with anyone. It doesn't matter if you're using Creo, SolidWorks, Autodesk, or CATIA. Our simulation software can plug in easily with just about any CAD platform without any problems. Now, I've been using the word simulation a lot, and some of you might be thinking, okay, great. Simulation, that's all well and good, but what does this have to do with me if I don't know how I can use it? Well, I'm here to tell you that you can use simulation. I work with a lot of companies that use ANSYS all the way from their first design sketches all the way up to when they're cranking out production parts. You'd be amazed at what is possible by having a conversation with one of our applications engineers. Some of the things listed here give an idea of how we can help. We work with autonomous vehicle companies all over the world to help them reduce their validation time from what would be 10,000 years down to just 2 to 3 years with some of the simulation capabilities that ANSYS can provide. Part of this is that our simulation results are now accepted by the FDA, FCA, and many ISO certifications that would normally require months to years of testing. So with that, I hope I've given you some useful background information on EAC and ANSYS. And with that, I will turn it over to my colleague Rod Scholl to start talking about some of the specific products that ANSYS offers.
Thanks, Vinny. This slide shows basically the suite of products that are within the ANSYS name set. And this still is sort of an introduction to the tools in the EAC, but I like to present it because for me, this slide is more of a technical slide than a sales slide. So having done simulation for 20 years or so, on the service side, on the training side, mentoring, of course, there's also sales support and scoping, that sort of thing. But one of the major benefits that I've always seen in the ANSYS package is scalability. So for any particular technical challenge, I think we've all had situations where we start with one tool, and as we progress, we eventually reach the limitation of a tool set. And when that happens, it means you either have to not answer the question or not answer to the fidelity desired, or you have to switch to start over in a more advanced tool set. And over the years, I've noticed that the cost of switching from a lower end tool to a higher end tool is expensive. Not only do you have to now learn two different tool sets, but there is, of course, building the model over. So if we were to add up dollars over time, I think what's most important from a simulation package is something that you can start with perhaps a lower end with cost-effective license to solve your particular problems. But when the day comes that you have a more challenging problem, such as orthotropic material properties or advanced nonlinear contact or impact simulations, things that aren't readily solved in a lower end tool, that you can either activate more licensing or leverage existing licensing which your company already has and not have a hiccup in the project. So this slide kind of shows that if you're in the structural domain but suddenly you have fluid load that you want to consider, then you don't have to change products in order to take those into account. Maybe you're doing structural analysis on the motor that wants to include EMAG, or maybe you're doing EMAG and structural analysis but now want to predict acoustic levels, engine noise, to not have to start over and start sourcing new software packages, but instead to just change licensing levels, I think is the most cost-effective part of the ANSYS suite, and it's its biggest selling factor. Of course, it's also got the the best capability, but that scalability I wanted to touch on. This slide shows us sort of some naming levels within the ANSYS tool sets. So oftentimes the names change for all these packages over time. I don't want to spend a lot of time on it, but I want to, this dovetails into the previous slide, show that you have a basic capability solution called Discovery Live. It's more of a designer's type tool. It's very cost effective. You can do very quick analyses with it, but fidelity is somewhat limited. There's a middle end tool called Discovery AIM, which can do everything from fluid flow, mechanics, blow molding, etc. But not all the bells and whistles are implemented and turned on. And then you have these ANSYS flagship tools. But again, this slide just sort of shows that you can start in one tool and expand through the tool set as required, and maybe clears up some different naming differences. The webinar today, we didn't want to focus purely just on ANSYS. We want to essentially have a technical conversation about modeling fatigue. So although ANSYS is my tool of choice, I think what we're presenting today will be useful to anyone doing fatigue analysis in any software package. So with that said, oftentimes when we're evaluating something in FEA, the generic question comes back from design or marketing or somewhere of, is the product strong enough? And that generic engineering term, strong enough, doesn't really classify the problem. And oftentimes people will then compare FEA results to yield strength. I think it's something that we all did back in school, to just use yield strength as sort of a universal criteria for evaluating a design. But if you've done much simulation or have much experience on the subject, you soon find that there's always a little bit of material yielding. If you tighten down a nut, you get some yielding at the interface, local yielding. And so the yielding is the issue. Really, what we're worried about is large scale yielding. And so the problem is never as simple, and that's even on the strength side. But then what we find is that many of our products actually don't fail in strength. In fact, I'd say the majority of them actually fail in a fatigue type situation. Sometimes things are under designed where we would buckle or shear, or the loads experienced are higher than anticipated. But oftentimes things fail through repeated loading, time in the field. You get a crack which initiates and then propagates. And that was sort of the impetus for this webinar, is to first differentiate between those two, which probably isn't news to anyone. We're just sort of clarifying here. And then talk about how to start doing fatigue failures prediction in your current design system, how you might get started in that, and what the topics of interest are in that domain. I will, add the qualifier that we have, a lot of different attendees on this call, and I'm sure there's a huge range of experience of those who have never thought about fatigue to probably fatigue experts. And so we try to add a little of everything. So hopefully not too much goes over your head, or if it's stuff you've already known, we hope you still glean value from some of the later slides where we get into more advanced topics. Obviously, you could do a fatigue webinar that would take a week long, 8 hours a day, and still not exhaust the subject. People spend careers specializing in this, so we can't cover it all in 45 minutes, but we want to introduce some of the major topics. Just driving home again the different types of failure modes. The picture's worth 1,000 words, I think, and so I kind of want to, pass through these. For the strength failures here on the right, you have your buckling type failures, you have burst failures and components, and then you might have a full-on failure, such as shear or, crushing or tensile failure. Now, on the left-hand side, most fastener failures are usually fatigue-induced, and cracking in small fillet radiuses also are generally a fatigue-induced phenomena. And finally, most welds also fail due to fatigue cracking. Usually once we start thinking about fatigue, it doesn't take long before we realize that most fatigue occurs at a joint. Either it's going to occur at a fastener or it's going to occur at a weld. Once in a while it occurs at a fillet radius, and so we always need to check that. But the problem becomes difficult quite quickly because fasteners and welds are something that are actually pretty complicated. Of course, fatigue is important to capture. There's tons of historical scenarios where fatigue wasn't considered, and current estimates now is at over 600 billion a year in industry losses due to fatigue type failures. And I wanted to mention fatigue forensics. So you might be in a situation where you're not sure how much things are failing in your industry or on your products due to strength or fatigue. Or maybe you're sure but haven't been able to generate an audience that has the same interest in predicting fatigue in your product set. Sometimes one has to sell the concept of simulation and its cost effectiveness in improving products and in the end driving revenue. Fatigue forensics is something you can do to do that. Take a failed product, put it in an SEM, and actually show, especially if it's steel, you should be able to see the beach marks and fracture, crack growth, and find striations maybe down to the micro level, and then finally fast fracture at the end. And so sometimes a picture's worth 1,000 words. You can for $100 give an SEM on a failed part, and then I think put a picture to the actual mechanism. And that's a good precursor to say, okay, now that we know the mechanism, let's start simulating to predict it so it doesn't affect us adversely. All right. For fatigue loading, obviously it's a repeated loading. We're thinking sometimes about full reverse load, where it's going to go to a positive value to a negative value and resonate back or alternate back and forth. Oftentimes that's from vibration and resonance. Other times you might have a non-constant amplitude, such as, you know, you're mounted on on an overroad vehicle or an aircraft or something with a non-constant signal. So there is some load definition and that needs to be accomplished so that we can cycle count and add up either of these scenarios to assess the fatigue life due to them. And so you probably, instead of talking about life in absolute, you know, years, oftentimes one refers to damage, which is a variable where you'll do a little bit of damage in this Dewey cycle. You can add those together via, say, Miner's rule. But obviously one needs to understand the loading environment and the changing loading environment in order to assess fatigue. Hopefully we've all seen SN curves before, so I don't want to spend a lot of time, but it's nice to see it on screen again, that you get a certain number of cycles, you have a maximum, you know, you can index for a given stress, you can come across and come up with a prediction of what the life would be for that stress. The common mistake I see in industry is people using that SN curve without taking into account that those specimens, generally speaking, used to generate such a curve were smooth, polished specimens at room temperature. Whereas what we have is usually an unpolished specimen, and there's also going to be variability in the field. If you have 1,000 products, sometimes 1 in 100 failures isn't acceptable. So you can see I've got a list up here of surface finish, reliability, temperature, some size factors, environment. There's all sorts of other what we call knockdowns that need to be applied to adjust this curve. So that's a cautionary statement that don't just pull a stress out and run to this curve, or you're going to be off probably dramatically in your predictions of the actual field life. Because of the log nature of this scale, I'm going to throw out a rule of thumb that a 30% difference on stress is a 2x difference on fatigue. So if you double the stress, you can, you know, have dramatic changes in fatigue life. It's not a direct relationship. This isn't a very good rule of thumb because you're trying to extract a log scale relationship, linear relationship, but it just drives home sometimes the point that if you have even a 15% difference in stress, that isn't trivial. That can dramatically change your product performance. It also requires a lot more fidelity in the FEA analysis approach, whereas in a strength calculation, you just need to get ballpark because you're usually yielding through a cross-section. With fatigue, you're trying to predict highly accurately stresses at a small location. That would be potential fatigue initiation. Endurance limit is a concept. If you look at those fatigue curves, as you follow that fatigue curve out, eventually some materials will flatten out, where there's a stress that if you stay below that stress point, you will have infinite fatigue life. You can load it all day long, and the product won't fail. Other environments, the corrosive environment, or say some aluminum and other metals, there is no safe amount of stress. One always has to do a fatigue calculation because you can add up 10 to the 7 cycles pretty quickly if you're resonating at 50 hertz, like maybe in a matter of weeks. So endurance limit isn't always something you can apply. So sometimes you can't just predict stresses and compare it to endurance limit. Sometimes you actually have to go the further step and predict fatigue life. Just checking the time here to make sure I don't talk too long and rob us of seeing things if we're doing good. If we look closer at these SN curves, there is sort of 3 regions where you have, if you have very high stresses, you can fail the product quite quickly. And then there's a middle region where it's fairly a straight line on a log scale. So you have a direct relationship between failure life and input stress. And then there's endurance limit where it flattens out. What I wanted to point out was that because of this straightness of the flat line, here at the endurance limit, it turns out there's a pretty consistent relationship between the stress level of that endurance limit and the ultimate tensile strength of the material. So I've seen a lot where people will compare it to yield stress and just say, well, we don't do fatigue evaluation, but we just compare it to yield, and we call that good enough for our products. That's always worked. And that's perhaps true for their particular product set. But really what makes more sense is if you're just going to do a back-of-the-envelope approach is to compare it to ultimate tensile strength. That's what fatigue endurance limits are proportional to. Not yield strength. So if you harden a material, the yield strength changes dramatically, but the ultimate tensile strength doesn't. And you'll find similarly that you can harden a material, change the yield strength, but you're getting roughly the same fatigue performance out of that material. So switching over to at a minimum to tensile strength, ultimate tensile strength rather than yield is maybe your first step towards improving a very quick approach to fatigue evaluation. And these constants are maybe you've all seen before. So under steel, 0.4 is the number a lot of people use. 0.357 is a little more accurate for the ratio between endurance limit and ultimate tensile strength. And aluminum is even lower. And so different materials you'll find will have a pretty consistent ratio between those two values. I mentioned before that you can't necessarily start with an SN curve and then index stress right away. You have to apply these knockdowns. It would take quite a bit of time to go through each of these knockdowns, so we don't have that, but I wanted to put them on screen and talk about them briefly. For example, whether the specimen is machined, hot rolled, forged, corroded, polished. There's different ways to index, and depending upon this, you can index the tensile strength of that material, what your surface finish is like, and eventually come up with a correction factor. So just as an example, if we take 120 KSI tensile strength, we come to a machine specimen, you can see we have a surface factor around 0.7. So you've already lost like 25% of your allowable stress, just taking into account the machining and that it's not a polished specimen. So it's a non-trivial thing to include. And reliability factor has the same thing. It drops things down by easily 20%. So by the time you add in your safety gear knockdowns, you usually take, let's say your allowable stress on the specimen was 100 KSI, which is, I guess I know a big number, but then by the time you do a knockdown, it's going to drop down to about 40 KSI. You're going to lose more than half of the allowable stress that you get off an SN curve. A good place to start to understand all this and delve into it is Shigley's much celebrated book. And it's a pretty clear listing of all the different knockdown factors and how to get started in each one of them. We should talk about the Goodman diagram. I think it'd be remiss to not include that. We know that you can have a mean stress. If your mean stress is at ultimate tensile strength, meaning the background stress, you're going to fail without applying anti-vibration. That's just called a tensile test. So if you don't have any background stress, but you have a large alternating stress, and that will also fail. Often we're in a situation where we need to know it's got a background stress of 20 KSI, but it has an alternating stress of 10 KSI. The Goodman diagram is what lets you take into account the mean stress of your product as well as alternating stress. So a good fatigue analysis will analyze both. You'll analyze the as installed, as built stress, perhaps with bolt pretensioning or thermally induced stress. And then on a separate analysis, you'll come with alternating stress and combine those two together. So typically within the ANSYS tool set, there are SN curves that are built in. You can also add them yourself. So this will save you from having to build a dramatic spreadsheet trying to do these calculations. That's a lot of labor for something which has been automated in most tool sets, or a lot of tool sets. And within ANSYS, and also with augmentation with grant materials, you'll find quite a bit of data is already in the suite. You just need to specify the material, and then it will start predicting fatigue life for you. And it'll even walk you through some of the knockdown factors. ANSYS has a built-in fatigue tool, so these steps will predict damage, or this tool will predict damage. It'll give you safety factors. You can do it with a stress life approach or a strain life approach that we probably won't get into, but it's just different types of SN curves. You can specify different loading applications, whether it's what the mean stresses are, if it's a constant load, or if you have a load history. So we've talked about a lot of different subjects already. I think it's always nice to have a tool set which is aware of those subjects so that you can sort of walk you through it, or at least let you know you're on the right path. And ultimately, what we're trying to do with simulation is communicate results to other stakeholders. And that picture always helps with that. Pulling out XY plots doesn't always go over so well. But something about a colored plot communicates. And so sometimes the end product of all of this analysis is that instead of producing a stress plot, one can produce a fatigue-like plot. So in cycles or months or days or years, you can say, in blue is where it's going to last forever, red is where it's going to break in a month. That often communicates to various stakeholders. And some industries use safety factor. That's an option as well. So there's easy fatigue, where we can just compare the UTS and a ratio. We can be a little more advanced and start predicting actual cycle life. By the time you get to either strain life, or if you have very complicated loadings, multiple different environments, load histories, different products, welds, you reach maybe a need for a higher end tool. And pretty much the highest tool out there is nCode, which is in the ANSYS suite. So obviously we can't get into everything there, but we did want to point out that it's the ANSYS scales to the most complex fatigue problem that you're going to encounter. And it's automated. There's a nice GUI. It's integrated into Workbench, and so can walk you through the steps, taking a lot of the labor out of doing these types of analysis. If you do any amount of fatigue, especially if there's a load history or you have a lot of different materials, I would recommend nCode, and just save you time in the end, save you money in the end. To talk about specific tips for FEA, obviously we don't refine the mesh to add infinitum to resolve the stresses. They go up over time. 6 elements per fillet is a good rule of thumb. And if you need to go further than that or justify it, you can always do a mesh convergence study where you increase that density and show how the stress is going to change much. I wanted to point out there is another method of having to, you can avoid that by using the PRERR statistic. You can read about that. That's a specific ANSYS term, but if you read it, that may be available in other packages as well. This will let you predict how much energy it's been captured, how much discredit, or how much difference between one element and the next that you're getting, which will tell you whether or not you have an adequately refined mesh. Given that a small percent difference in fatigue stress or in stress has a big difference in fatigue life, we need to take this kind of thing into consideration when doing analyses of fatigue as opposed to just stress analyses. Of course, you get into scenarios with singularities, such as a applied point load or a boundary condition we're holding on a point, or where there is a sharp line in your model. Sometimes it's not feasible to go into your model and add a fillet at every location. It just takes too long. So in those cases, there's a few different workarounds I want to point out. Of course, going and adding, like doing an analysis to kind of find rough high stress points and then go back and add fill to those locations is perhaps the most cost-effective approach. Another thing you can do is to include material plasticity. So although it'll be unrealistic at the corner, it's yield out and you'll have a region of yielded material. That's a common, easy way to address singularities. You can change your boundary conditions. Obviously, trying to avoid point loads and point constraints is a big factor. But the last one, most powerful tool, and one that I pretty much usually use at this point, is stress linearization. So stress linearization is a fancy sounding term to go through a particular point in your model and to extrapolate the stresses along a line and come up with to curve fit a linear line through that location. This is used to predict what the stresses will be, say, at the toe of a weld or at a fillet with that you didn't explicitly model. And then there's this hotspot method, which is a pretty refined approach to where to take your data points, how to extrapolate. So if you find yourself in a situation where you have a sharp corner or you have weld, you're going to want to familiarize yourself with this hotspot method to evaluate those welds. There's, in the last 15 years or so, there's been an explosion of people interested in predicting fatigue in welds and in small fillets. And so you'll benefit from delving into this subject. Well, we'd be a little remiss to not talk about bolt fatigue. I've got one slide in here because I want to leave it out, but obviously that's a huge subject. So if you find yourself in a situation where your bolts are what's failing first, that's probably a good design. That's the intent of bolted structures, is the bolts go first because those can be replaced. To predict that behavior, you're going to want to rely upon a standard. It's pretty rare to have an FEA model of some threaded fasteners where you're trying to predict a thread in the root of trying to predict stress in the root of a thread. So you're going to want to use a standard. I've thrown a few of them out there. SME, I like the S7608, AISC, IW, where you'll get a allowable mean stress for the bolt and alternating stress, where you don't have to know the stress in the fillet, but just the average load going through the bolt. And they've used component testing to determine how long a bolt lasts. Shigley also has an approach, which many industries just use that. List off the grade of the bolt and tell you what the allowable load basically is, or average stress is for that bolt. And Shigley also shows a more involved approach. So we can't get into all that there, but those are some keywords to get you started down that path. For weld fatigue, again, that's a long conversation, but there's some standards. IIW, again, BS7608, ASME, and AWS are all ones that you might want to start with one of those. They're growing together. They originally started out in different locations, but they're all kind of arriving at the same methodologies, including the hotspot method I mentioned. I bring it up because there is a more accurate tool called the Verity method. I don't see that so much in the industry. That's more for if you really need to refine the accuracy, but it is more accurate than the above methods. It's just more costly to implement. So if you're using the above methods and want to go one step further, move toward Verity method, but I wouldn't start there. For welds, you're going to want to use the hotspot method of stress linearization. You can see they've got green line is one query, yellow is another query, red is where they're predicting stresses. To do that by hand everywhere in if you have a welded structure, it's going to be very laborious. So you're going to want a tool set that does it automatically. So automation is key to evaluating weld fatigue, and ANSYS has the best tool set for that. In some ways, you could say it has the only tool set that does this in combination with the FEA in a robust manner. So if that is of interest to you, it's something we can have the conversation and put those tools in front of you to see how applicable they are. Lastly, I just want to throw up a slide for areas for more learning. I've touched on a lot of subjects. Hopefully some of them were new. Hopefully it also wasn't overwhelming. If you want to go further, this is the next thing to research. Is of course the fatigue knockdowns we talked about. So you take an SN curve and apply it to your particular situation. Learn how to take your load cycles and cycle count. If you have this red graph here, trying to add all that up into a load history is something that you're going to use a tool for. Rain flow counting, for example. Bolts and welds and bolts and welds. I mean, that's a big subject, but we have a lot of industry experience. We're welcome to speak with anyone on the phone to give some advice just in general and as well as on what tool sets might apply. If you have low cycle fatigue, high stresses, but not a lot of, maybe it's failing at 5,000 cycles, not 5 million, you might switch over to strain life fatigue. So normally we all learned about stress life fatigue in school. There's something called strain life fatigue, which is more accurate when dealing with very high stresses. So instead you look at the strain of the material, and it's expecting there to be some plasticity already. So if you're yielding in your component with each cycle, you probably want to switch to the strain life method. There's something called knot sensitivity effects. It's often ignored. I won't even go into it. It's worth Googling, but it's a credit that will give you longer predicted fatigue life that people don't take advantage of always. But basically, if you have a tight fillet radius and a really high stress concentration, things aren't as bad as they seem. The tight fillet has a notch effect that you can kind of dial down your stress a little bit by taking into account notch sensitivity effects. And then finally, there's actually predicting crack growth. I've heard it said that half of the life of a product is in crack initiation and the other half is in growth. Obviously, it varies per the situation. But many times you can get away with the crack, and if your product's thick enough, you still have a couple of years left before the crack propagates. You wouldn't want a safety situation, but sometimes there is no safety situation. So people will predict the life of a crack. The ANSYS tool set is premier in doing that. You can see off to the side the actual model of the crack as it propagates through a structure. So if that's of interest to you, we can talk further about that. All right, well, with all that said, I think I'll turn it over to Vinny. I think maybe a lot of time, Vinny, but hopefully enough.
No, that's okay, Rod. You already kind of prefaced a lot of what I was going to say, but just want to emphasize that here we are more than happy to walk through with any of your technical challenges that you're experiencing to help you design any kind of solution that suits your needs, whether that's looking at a specific software package or whether it's just looking at some engineering servicing work that you want to submit to us. We can provide anything that you'd need in that range. Like I said, whether it's pricing on a new package, whether it's pricing for servicing, or if you need training or education, we can also provide you access to get your hands on some of those materials that you might need. And I have included my contact information underneath here. If you guys have any questions, I'm always available day or night through my cell on there in case you can't get a hold of me at work and in case I'm traveling. So if you have questions, I'm happy to talk. And Cassie, I think we were going to look at a couple of questions maybe to come into the queue now, I think, correct?
Yes. If anyone has any questions that they want to send in, go ahead and do that now. Otherwise, we'll go through a few that we've got prepared here. And
yeah,
Rod, I'll let you go ahead and.
Yeah, I was supposed to mention that sooner so people had time to write them in. So we'll give that in a minute. I see some are coming in now. So we'll get to which ones we can, especially ones that seem universally applicable, and we can hang on for a while here so we don't have to have a hard stop. But those of you who maybe do have a hard stop, we certainly appreciate you attending. We also hope you got some value out of the presentation, and we look forward to continuing the dialogue and maybe doing more of these in the future. You know, some of the feedback we can receive is what else you'd be interested in and seeing and learning about. We try to be a technical partner, and that includes, sharing expertise. And then if we get a dialogue going, we can learn more about your particular challenges, your industry. So I think everyone benefits from more of these in the future. Okay, so here's a question. It's where can I find fatigue data for our specific materials? Right. When we do service type work, we have to budget for that step because it's not always that simple. There is this Granta materials database that you could look up, and we can provide access to that software. It has an index of, I don't know, let's say 1,000 different materials, including fatigue life for many of them. I don't even know the number, maybe it's 10,000. It's just a lot. What's surprising is not necessarily every material is covered, but depending on heat treat and everything else, that you really need to dial in your material much more so than you would on a strength. Strength, you just have to yield UTS, maybe you need modulus Poisson's ratio. But for fatigue, you'll need to know the heat treat, you'll need to know similar properties. So in that case, you have to use Google, and we can help you move forward with that.
And I actually saw a couple questions come in the queue, Cassie and Rod, maybe this is more for you, asking if either the slides would be available for download or if they will be sent out.
Yes, I will be sending the presentation slides and the recording of the webinar in an email this afternoon. So you will get that if you would like to look over the presentation again or send it to your coworkers. I do have another question that came in. Possibly, Rod, you can answer this one. It says, is the software applicable to plastics?
Yes, for sure. So I've talked a lot about metals, and maybe I'm remiss in having done that. A lot of products are plastic, and plastics behave very similarly. They also will have a fatigue curve. They'll have an endurance limit. And so there's not a lot of difference in approach applying for plastics. Oftentimes, the yield range. So you have to model in with a linear analysis, but a nonlinear analysis predicts the true deformation of a plastic component, whereas in metal, usually the deformation is not high. But the fatigue process is mostly the same. It's just a matter of having the right fatigue properties, and as I just mentioned, perhaps including a plastic analysis, meaning plastic material properties. So not like polymer plastic, but high deformation, yield, past yield. So you'll probably want to include that when you're modeling, plastic polymer type materials.
Great. Can you guys hear me again?
Yeah.
Okay. So another question came in. Can you run a fatigue analysis with a pre-stress of a compressive stress?
Yes. Good question, because we talked about a lot of things. A lot of products fail at fastener location, welds and bolts. And if you were to tighten down a bolt, you generate usually compressive stress in that region. And what we'll find is things don't really fail if you're in compression. If you're going from zero stress to compressive stress, that doesn't open cracks, it tends to close cracks. So there is a point where you can still fatigue it in compression, but generally speaking, you want to take for that compressive background stress. So we've talked about two steps in the fatigue analysis. You have to first model background stress, and that's your mean stress, and then you also have to then model your alternating stress. It's often two different analyses. So to answer the question, yeah, it's a good approach to take into account any initial compressive stress. In ANSYS, it's relatively easy to install bolt-free tension. So if you've defined connected regions, I urge you to go through and to select those connected regions, be it the actual bolt, the circular areas, put in stress load there at assembly, and then come up with your prediction for what your average back stresses are before proceeding to the stress.
Great. I think we have time just for a few more. So we've already gone over, but I did just want to thank those that are still on, and I do understand if you have to hop off, and any questions that are unanswered, we'll reach out to you after the presentation. Do you guys see any more questions that you'd like to answer before we hop off?
Yeah, I think you're breaking up, Kathy. Is that right, Vinny? Is that her?
No, it might be her because I'm hearing her all right. I think one other question, Rod, that I think would be good to cover that I saw come in late was how do you automate weld joint analysis?
To automate the what?
How do you automate weld joint analysis?
Yes, I mean, if you have a single weld location, that's difficult. But if you have a lot of locations, is a weld fatigue tool within ANSYS. And without that, that's the only way to do it. And this is actually a relatively new tool. There's a couple others out there that I've investigated over the years, and they just don't pair well. So if you have more than a couple of locations, I'd say let's have the dialogue. We'll introduce you to that tool. It's relatively cost effective. It's not that expensive, especially if you're already using ANSYS. So we can introduce that to anyone.
Great. I think we are going to wrap it up just because we are over a few minutes here. But thanks again so much, Vinny and Rod, for that presentation. And thank you guys for sending in your questions. I will, again, be sending the recording of the session in a follow-up email this afternoon. And then the short survey will appear after the webinar is shut down. So please take a minute to answer those for us. So thank you again, everyone, for reaching out and attending today, and have a great rest of your day.